Hello friends, welcome you all to the sixth lecture on function analysis and its applications. In this lecture, we will discuss on nonlinear space, pseudo-normed linear space with examples. The contents of today's lecture as follows. Nonlinear space. Let X be a linear space, that is vector space, over the field K either R or C, set of real number or complex number. A function this such that X to R is said to be norm on X. This function is known as norm if satisfies the following conditions. First, norm X greater or equal to 0, that is positive. Norm X equal to 0 if and only if the point X equal to 0. Third, norm AX is equal to mod A norm X for all X belonging to X and A scalar. And fourth property, norm X plus Y less or equal to norm X plus norm Y for all X, Y belonging to X. Some authors this mapping written as norm such that X to R0 plus, that is R0 plus equal to 0 infinity, means norm X greater or equal to 0 but not infinity. So if we avoid first condition, so we can write norm such that X to R0 plus. Then the function this point, this is the X point X, is called norm on X, and the pair X and norm is called nonlinear space. Okay. The real number norm X is called norm of the vector X. X is the element of X. Why? Because here small x is the element of X and mapping this known as norm X is the element of R, that is R0 plus. If we drop this condition second and other conditions satisfied as it is, and second condition can be written as norm X is equal to 0 even if X not equal to 0. That is, we may have X is equal to 0. This implies that norm X is equal to 0 but not conversely. Not conversely means norm X is equal to 0, then X is equal to 0 not necessarily. So if satisfy the second condition in this way, then ordered pair X norm is called semi-normed linear space or pseudo-normed linear space. From third property, if putting A is equal to 0, here third property, norm AX is equal to mod A norm X. If A is equal to 0, that is norm 0, AX as vector, okay, and mod A, that is scalar, and norm X, this is X is vector and norm X real number. So norm of 0 vector is equal to 0. Okay. Here, if A is equal to 0, that is norm 0, A 0 into x, that is norm Ax is equal to mod A norm x, that is mod 0 norm x, that is 0. Okay. Why we have taken mod A? Because distance always positive. Okay. So we have to write right side and always greater or equal to 0, that is A is any scalar, may be real or complex. So mod A always positive real number. So we have to write mod A because this will be positive. 0 is equal to norm x minus x. We can write here x plus y. So putting y is equal to minus x. Then this can be written as x plus minus x less or equal to, applying force property, norm x plus norm minus x. Again we apply the third property, norm alpha x is equal to mod alpha norm x, that is mod alpha norm x, that is here alpha is minus 1 and x vector, so mod alpha norm x, that is mod minus 1 1, so norm x plus norm x, that is 2 norm x. So here this is 0 less or equal to 2 norm x. Therefore norm x greater or equal to 0. So norm always positive value or 0. For example, the real linear space is non-linear space with the norm this such that R to R defined by norm x is equal to mod x for all x belonging to R. Okay. Then ordered pair norm R is a non-linear space. So let us check one by one property of norm. For any x belonging to R, norm x defined by mod x, that is mod x, and we know that mod x always greater or equal to 0. Hence norm x greater or equal to 0. First condition satisfied. Second, for any x belonging to R, we have norm x is equal to mod x. Thus norm x is equal to 0. Let norm x is equal to 0. Norm x defined by mod x. It means mod x is equal to 0. So mod x is equal to 0, and we know that mod x greater or equal to 0 if mod x equal to 0, we have if and only if x is equal to 0. It means norm x is equal to 0 if and only if x is equal to 0. Okay. Third, if A be scalar, then norm Ax, norm x defined by mod x, that is norm Ax is equal to mod Ax, and we know that mod Z1 Z2 is equal to mod Z1 mod Z2. So mod Ax can be written as mod A mod x, and mod x is vector, so mod x can be written as norm x. So norm Ax is equal to mod A norm x. Third property also satisfied. Fourth, norm x plus y equal to mod x plus y as per statement, and we know that mod x plus y less or equal to mod x plus mod y. Here xy belonging to R, that is vector. So mod x, mod y can be written as norm x, norm y. That is norm x plus y less or equal to norm x plus norm y. This one. Okay. So pair R norm is a norm linear space. Next example, the complex linear space C over C is non-linear space with the norm defined as follows. Norm Z is equal to mod Z. If Z is equal to x plus iy, then mod Z is equal to square root of x square plus y square. Okay, mod always greater or equal to 0, that is we have to take only positive value of square root. So we have to check one by one all properties of norm. Here defined norm Z is equal to mod Z, that is under root x square plus y square for Z is equal to x plus iy. So this is greater or equal to 0, then we can say that norm Z greater or equal to 0. That is norm Z greater or equal to 0 for all xy belonging to R. In this case, Z is equal to x plus iy, x and y as individual belonging to R. For any Z belonging to C, we have norm Z is equal to 0. Norm Z defined by mod Z. It means norm Z is equal to 0 if and only if mod Z is equal to 0, where mod Z is under root x square plus y square. Okay, this is possible when x and y 0. That is Z is equal to 0 plus I0, that is 0. Therefore, norm Z is equal to 0 if and only if Z is equal to 0. So second condition satisfied. Third, for any scalar A, suppose A is equal to B plus IC, I means iota, under root minus 1. For all BC belonging to R and Z is equal to x plus IY for all XY belonging to R. Then we have norm AZ. Norm AZ, as per statement, we can write mod AZ equal to value of A is B plus IC, value of Z x plus IY. So we can write after multiplication Bx minus Cy plus I into By plus Cx. So this is also a complex number, and this is the modulus value. So we can write square root of the square of Bx minus Cy plus square of By plus Cx. Okay, expanding this using the formula square of A minus B and square of A plus B. So we have square root of B square x square plus C square y square plus B square y square plus C square x square. So taking this term and this term, taking common B square x square plus y square. From this and this term, we take the common C square, we have y square plus x square. Again, we have two terms, so common x square plus y square, we have another term b square plus c square. So we have b square plus c square under root and also the square root of x square plus y square. So this term can be written as modulus of b plus ic and this term modulus of x plus iy. Therefore, this can be written as a as defined b plus ic is equal to a. So mod a and this is mod z. So z as vector. So this is mod a norm z. So norm az is equal to mod a norm z. Third condition satisfied. Fourth condition, for z1, z2 belonging to C, we have square of norm z1 plus z2. Norm here defined, norm z is equal to mod z. Then we can write square of norm z1 plus z2 is equal to square of mod z1 plus z2. So square of z1 plus z2 can be written as z1 plus z2 and conjugate complex of z1 plus z2. z1 plus z2 bar can be written as z1 bar plus z2 bar. Multiplying z1 plus z2 and z1 bar plus z2 bar. So z1 bar plus z1 z2 bar plus z2 z1 bar plus z2 z2 bar. We know that z bar is equal to mod z square. So applying this property, z1 bar is mod z1 square and this z1 z2 bar and this can be written as z1 z2 bar whole bar, that is conjugate complex of z1 z2 bar. Okay, and this one applying this property, that is mod z2 square. Okay, also we know that z plus z bar equal to two real part of z. Let z is equal to x plus iy, z bar is equal to x minus iy. Then z plus z bar equal to 2x. That is two real part of z. Okay. So this term can be written as two real part of z1 z2 bar. Okay. Now again, using the property real part of z less or equal to mod z. Real part of z equal to x if z is equal to x plus iy and mod z equal to under root x square plus y square. Okay. So here clearly real part of z less or equal to mod z. And also we know that mod z is equal to mod z bar. So this term, using this we can write square of the norm of z1 plus z2 less or equal to mod z1 square plus 2 mod z1 mod z2 plus mod z2 square, using this property. This all term can be written as square of the mod z1 plus mod z2. Okay, taking square root of both sides, we have norm z1 plus z2 less or equal to mod z1 plus mod z2 and norm z defined by mod z. So we can write mod z1 as norm z1 and mod z2 can be written as norm z2. So norm Z1 plus Z2 less or equal to norm Z1 plus norm Z. Thus, order pair C and norm is a non-linear space. Next example. Consider the Euclidean space Rn. If x equal to n tuples of x1, x2 and so on xn and y is equal to y1, y2 and so on yn are 2 points of Rn, we can define norm on Rn as norm x1 equal to summation mod xi. I is equal to 1 to n. Then the ordered pair Rn and this norm notation norm 1 is a nonlinear space. How to say this pair is a nonlinear space? Let us check all properties of norm. Okay. Explanation. Given the space Rn and the function norm x1 defined summation mod xi. I is equal to 1 to n. For any vector x is equal to x1, x2 and so on xn. First, norm x1 greater or equal to 0, that is always non-negative, because mod xi greater or equal to 0. Here norm x defines the summation of the mod x1 plus mod x2 plus and so on mod xn. It means sum of n non-negative numbers. Okay. So sum of all non-negative numbers is non-negative. That is norm x1 greater or equal to 0. Okay. Thus x1 is always non-negative. Second property, if norm x1 is equal to 0, norm x1 defined by summation I is equal to 1 to n mod xi. Okay. Sum of the n terms of non-negative numbers. If norm 0 and summation of mod terms 0, it means each xi 0. Okay. Each xi 0 means x1 0, x2 0, xn 0. All 0, it means this is the 0 vector. Okay. So if x1 is equal to 0, if and only if x is equal to 0, that is 0 vector. Okay. Here detailed explanation, mod xi greater or equal to 0, mod xi equal to 0, if xi is equal to 0, okay, this implies that x is 0, 0, 0, that is 0 vector. Conversely, if x is equal to 0, then each xi is equal to 0, individual 0. Therefore, norm x1 is equal to summation mod xi is equal to 0. Therefore, norm x1 is equal to 0 if and only if x is equal to 0. Third property, norm ax, where a is a scalar belonging to R and x is vector belonging to Rn, then ax, okay, if x is equal to x1, x2 and so on xn, x is equal to x1, x2 and so on xn, then ax is equal to a x1, a x2 and so on a xn. Okay. So norm ax equal to summation I is equal to 1 to n mod axi. Okay. So each term of vector Ax equal to Axi for all I is equal to 1 to n. Okay. So property of mod Z1 Z2 is equal to mod Z1 mod Z2. Okay, applying on this term, mod Axi is equal to mod A mod Xi. We can write this. Here A free from I, so we can write outside the summation. That is mod A summation I is equal to 1 to n mod Xi. And as per statement, we can write summation mod Xi as norm x1. Thus, norm Ax1 equal to mod A norm x1. So, satisfies the third condition. Fourth, triangular inequality. Norm x plus y under given norm 1 less or equal to norm x1 plus norm y1 has to prove. Here x equal to x1, x2 and so on xn, and suppose vector y is equal to y1, y2 and so on yn. Okay, then we can write x is equal to x1, x2 and so on xn, y is equal to y1, y2 and so on yn. Therefore, x plus y is equal to x1 plus y1, x2 plus y2 and so on xn plus yn. Okay, so we have the vector x plus y as n tuples of xi plus yi, where I is equal to 1 to n. Okay, so norm x plus y equal to summation I is equal to 1 to n mod xi plus yi, we can write. By the triangular inequality of real numbers, mod xi plus yi less or equal to mod x plus mod yi. Okay, so this less or equal to mod xi plus mod yi, can write, and summation in both terms, that is norm x plus y less or equal to summation mod xi plus summation mod yi. So as per statement, this can be written as norm x plus norm y. So fourth property, norm x plus y less or equal to norm x plus norm y, satisfied. Hence, we can say that Rn under this norm 1 is a nonlinear space. Example of pseudo-norm. Let R cube be the vector space over R. For x equal to x1, x2, x3 belonging to R cube, and norm x is equal to mod x1 plus mod x2. Okay. Then norm is a semi-norm on R cube, but it is not a norm on R cube. Okay. So as above example, we can prove easily first, third and fourth property of norm, but second property, this one not satisfied fully. For example, if x is equal to triplet of 0, 0, 1, then norm x as per definition, norm x is equal to mod x1 plus mod x2. Here x1 0 and x2 0. That is mod 0 plus mod 0 is equal to 0. So norm x 0, but x not 0. Therefore, norm x is equal to 0, x not equal to 0. Hence, R cube R is a pseudo-norm with the norm defined. Then, R cube with this norm is called a pseudo-norm. Theorem: every nonlinear space is a metric space. With respect to the distance function defined, dxy is equal to norm x minus y for all xy belonging to x, where x is a nonlinear space, that is vector space. Okay. Another way, if x be a nonlinear space and distance function from x cross x to R defined by dxy is equal to norm x minus y for all xy belonging to x, then D is metric on x. Let us prove it. We shall verify the axioms of metric space. Okay. So here xy belonging to x given, okay, and x minus y belonging to x, because if x belonging to x and a be any scalar, then ax also belonging to x. If b be any scalar, then by belonging to x. So here a is 1 and b is equal to minus 1. So sum of the two vectors is a vector. So x minus y belonging to x. So we can check the all properties of norm. So norm x minus y greater or equal to 0. Okay. First property of norm. And norm x minus y defined by dxy. So dxy greater or equal to 0. Second condition, norm x minus y is equal to 0 if and only if x minus y is equal to 0. As per the second property of norm, we can write it. And norm x minus y can be written as dxy as per the statement of theorem. Here, if and only if x minus y is equal to 0, that is x is equal to y. Hence, dxy is equal to 0 if and only if x is equal to y. Third property, norm x minus y equal to norm minus 1 y minus x, we can write by taking the common minus 1. Okay. So applying the third property of norm as norm ax equal to mod a norm x. Here a is minus 1. Okay. So this is mod minus 1 norm y minus x. Mod minus 1 is 1. So norm x minus y can be written as norm y minus x. This implies that dxy and this one dyx, that is dxy is equal to dyx. Fourth property, taking x, y, z all the elements of x. Then statement of theorem, dxy is equal to norm x minus y, norm x minus y can be written as x minus z plus z. We have added z and subtracted z minus y. So, applying fourth property of norm, this is one term x minus z and second term z minus y. That is less or equal to norm x minus z plus norm z minus y. Therefore, dxy less or equal to dxz plus dzy. It follows that d is a metric on x. Hence, we can say that every nonlinear space is metric space. Noting point, if we take y is equal to 0 in dxy is equal to norm x minus y. So, we get dx 0 equal to norm x minus 0, that is norm x. It means norm is a distance function also, but what is the difference between norm and metric? Norm is the distance between the point from the origin. Okay, and in metric we measure the distance between the 2 points. So, as per definition of metric, here norm such that x to r, this is also distance function, so we can write norm such that x cross x to r, but one x has the vector and another x should be the 0 vector. Okay, here clear that the distance function measuring from origin, x is the element of x, here dx y such that x cross x to r. Okay, x belonging to this vector and y belonging to this vector. Okay, so order pair xy is the element of x cross x. In norm, x such that x to r. It means this is the vector space x and this can be written as norm x such that x cross x to r. It has only 0, 0, 0, that is 0 vector. Next proposition, every nonlinear space, this order pair V norm is a metric space with respect to the distance function dxy equal to norm x minus y for every xy belonging to V. However, the converse is not true in general. For example, let x be metric space with the discrete metric. Consider D induced by a norm x minus y is equal to dxy. Here discrete metric defined dxy is equal to 0 and 1. 0 if x is equal to y and 1 if x not equal to y for all xy belonging to x. Is not a normed linear space. Since xd is metric space with the discrete metric, so if x not equal to y, then dxy is equal to 1. Now if A not equal to 0, then ax not equal to ay. So dax ay is equal to 1. Okay. By the third property of norm ax minus ay. A common, we can write norm ax minus y equal to mod a norm x minus y. If we take a is equal to half, then ax minus ay, that is norm ax minus y, equal to norm half into x minus y, we can write. Then by property norm ax equal to mod a norm x. So mod a half positive, so we can write half norm x minus y, that is half dxy. Okay. Since dxy is equal to 1 if x not equal to y. Okay. So norm ax minus ay is equal to half. Therefore norm ax minus ay is equal to half, which is not equal to 1. That is not equal to dax ay. So we cannot induce the discrete metric d by a norm. Translation invariance. A metric d induced by a norm on a nonlinear space X satisfies the following. D x plus z y plus z is equal to dxy. It means no variance after adding one more vector. Here x, y, z all are the element of nonlinear space X. Second, d lambda x lambda y is equal to mod lambda dxy, where lambda be scalar here, it should be lambda. Proof: dx plus z y plus z equal to norm x plus z minus y plus z, because d x y equal to norm x minus y. So here d x plus z y plus z, we can write norm x plus z minus y plus z. So z cancelled out, we have norm x minus y. So norm x minus y, that is dxy. So translation invariance. D of lambda x lambda y, here d x y is equal to norm x minus y. So here missing, it should be lambda x minus lambda y, and lambda common from here, norm lambda x minus y. Okay. So applying norm lambda x is equal to mod lambda norm x. So it can be written as mod lambda norm x minus y equal to mod lambda norm x minus y can be written as dxy. That is d lambda x lambda y equal to mod lambda dxy. And second proved. Next theorem. If X is a nonlinear space, then modulus of norm x minus norm y less or equal to norm x minus y for all xy belonging to X. Proof is very simple. Norm x can be written as norm x minus y plus y. Okay, that is no change. And we can apply the fourth property, that is triangle property of norm, that is less or equal to norm x minus y plus norm y. Therefore, norm x minus norm y less or equal to norm of x minus y. Similarly, norm y can be written as norm of y minus x plus x, that is norm of y minus x plus norm x. Okay, norm x minus y is norm y minus x. So this is here and this is in left side. So norm y minus norm x less or equal to norm x minus y. From 1 and 2, this is 1 and this is 2. In 1, norm x minus norm y, and equation 2, norm y minus norm x. It means we can write modulus of norm x minus norm y less or equal to norm x minus y. In this lecture, we have discussed nonlinear space and pseudo-nonlinear space with examples. These are the references which have been used in this lecture. Function analysis, Dover publications by George Beckman and Lawrence Narissi. Second, functional analysis with applications, John Valley and Sons by Erwin Krejcik. Third, function analysis, New Age International Publishers by V.V. Lemieux. Next, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you for your attention.